started. First of all, welcome to the mock interview. Glad to have you here. I believe it's the first time we've spoken about this, but let's just get right to it. So the format here is going to be an hour, like a real interview, and realistically speaking, you'll have about 45 to 50 minutes to do the problem. So that's sort of our target here, okay? And I'm going to
Yep.
have you control the time on that one, okay? So it's for up to you to look at the time. Um,
Okay, sounds good.
yeah, and then so we won't do introductions here. We'll just get right into it. In real interview, of course, you'll be talking a little bit. At the end, we'll save the 10 to 15 minutes for feedback and any questions you might have. Okay.
All right,
All
sounds
right,
good.
so let's just get right to it. So the first problem I would like you to write is a function called closest points. Okay, and the function is going to take in a list of points and an integer in. Actually, let's name it. Let's call it m. Okay, and these points are two-dimensional Cartesian points on the xy plane, and you are to
Hmm.
return me the m closest points to the origin in this original list.
Okay, gotcha. A list of two-dimensional Cartesian points. X, Y, I'll just call the coordinates X, Y, integer M. Could you remind me again what integer M represents?
That is the number of points that I want returned.
Okay. We want okay. And then we just want the M closest points to the origin. Okay, sounds
That's
good.
right. That's right.
Okay. I'm just gonna take a second to think here. M closest points. So I think for sure we have to check all the points. So at minimum, this is going to be an O of N operation. So I'm just trying to think right now, what is the criteria that we should check to see which one is closer? So I'm thinking Euclidean distance. So that would just be squared plus y squared, something like this. Okay, so then I guess like I'm just gonna work through like a naive solution first in my head. So we would go through each point and then kind of check Euclidean distance, and then we see whichever one is closest. We take the top m smallest values, and we would just return that. So I think the actual difficult part of this problem here is that we need an efficient way to actually obtain the top m smallest, I guess, distance to the origin. So I'm just trying to consider what's the best way to do that. Um, Obviously, the easy, like naive solution would just be to sort it so that we would pay in log n after we've taken all of the kind of the Euclidean distance, and then we just sort it, and then we just go through and take the top m. So that would be in log n. I'm just thinking maybe if there's like a better way to do this. Let's think. So maybe I should work. I'm gonna write down a small example first.
Mm-hmm.
Okay. Mm, okay, and then origin should always be 0 to 0. Okay. Um, are negatives okay? I guess negatives don't really matter, right? Because it's Euclidean distance. I feel like I might be missing something. I just need to make sure I don't get anything wrong with the problem setup. So Cartesian points, m number of integers. Are there any weird edge cases here? I can't think of any off the top of my head right now, so I'm just gonna
Okay.
keep going, and then maybe we might encounter one down the road. And one again. So let me just think. If we always take the Euclidean distance as 0, and then this one would be okay. So this would just be 1 squared plus 2 squared. So I'm just gonna write down the actual Euclidean distance for each point. This one would be 1, 4.
If I may recommend, you just pick easier points to make Euclidean distance.
Yeah, I don't think I actually have to take the square. Kind of just look at the value inside.
Okay.
Um, but yeah, I suppose these points are going to be right. They're going to be in the same order, anyways. Okay, let me think. Um, okay, no, I think I'm focusing on the wrong thing right now. Like the difficult point that I need to work through is not if how the Euclidean distance works. Like that's pretty obvious. What I need to think about right now is if there's an easier way to obtain the top m numbers. So maybe there's a way, I'm thinking maybe like a heap or something that I can like sort the values as I calculate the Euclidean distance. So like I can keep adding to the data structure and the data structure will keep ordering itself to maintain like the top and kind of smallest units. This reminds me kind of the there's a Leetcode problem I recall called K top K numbers or something like that, where you
Okay.
maintain the M or like K smallest numbers in the string. So I'm thinking if this would apply in this situation right now. From what I can recall, that was in that problem you use a heap, and then you would heapify it each step. You would push to the heap. And then the way is, I think the trick to that problem is you would make sure the heap is of size m, which is like the top amount that we want to keep track of. So this would still be in log in the worst case, but if our integer m is significantly smaller than n, I believe this would be an optimization over just sorting every single point after finding the Euclidean distance for each. So, okay. Does it kind of sound like I'm on the right approach, or do you think we could simplify this even more?
I mean, that sounds like it's. I mean, that sounds plausible, but do you think it's more efficient just in your head, or do you have some math to back that up?
Okay, so I guess I should kind of step through an example. So let's say we have n points, right? And then let's say m is like quite small. Like n could be like 10,000 or something, but let's say m is just like uh I don't know, just 15, right? So I need to essentially convince myself that this is actually a significant optimization here. So when we maintain a heap, so when we insert, we need to heapify up, I believe. Right, I believe it's to heapify up. So we would maintain a min heap in this case. And from what I recall, whenever we heapify, it costs log n because we need to traverse from bottom to the top of the, I guess, the heap tree. So then at most, if our tree only has a constant number of elements, so O of 1 elements, the heap is at, at most size O m. Usually it would be log n, but then I guess in this case it would be log m, I believe. So then at most m would be the same size as n, so we would run log m in times. Okay, so I guess the runtime is not even in log n at the worst case. It would actually be in log. Oh no, sorry. It would still be approximately in log n. But I believe that this would be a significant optimization, yes, over just sorting the inputs. Because we're
Okay.
essentially what we're
Yeah.
doing, like when we sort, like we're considering all of the elements together, but then using the heap data structure, because we're making sure its size is of only approximately m,
Okay.
we're only considering the minimum, like the exact subset of elements that we need to keep track of. And then in the end, we want the top m elements, we would just pop everything off the heap. So then that would also cost uh, essentially m log n, which is approximately in log n if m is very close to n. Okay, I'm just gonna think, did I miss anything else?
Sorry, can you just clarify to me
Um,
really quickly again what the m log m is from?
right, m is the number of points that we want, right? So m,
Yes.
we want the top m smallest points, or
Yes.
like points with the smallest Euclidean distance, which means they are the top m points closest to the origin.
Yes.
So our heap will keep track of just this for us.
Okay. Yeah. Go
So
ahead.
I think this approach seems fine for now. I'm just going to, I guess, start coding this up because I feel like I'm clear with how it works. And also, I'm pretty convinced that the runtime is an optimization over just sorting the inputs. So I guess I'll just start coding for now. And then if I encounter any issues, I can maybe revise my plan. So I'm just going to look up some of the Python heap stuff. Yeah, it's been a while since I've used this. Let's see,
Mm-hmm.
heap queue. All right, so Python has a heap queue. Do you need me to share my screen so you can see what I'm looking at?
No, I don't care.
Okay, gotcha. Min heap. Let's see, min heap. Okay. Um, heap queue. Okay. Where is the?
What are you looking for?
I'm looking for how to use a min heap, like the data structure. 'Cause I think Python should have one built in.
Yes, Python
Um,
has the heap queue library, which operates on an array structure, on a
okay,
list
gotcha.
structure. Yes.
Yeah. I'm just trying to remember, is it max heap or min heap by default? There should be an initialization setting to kind of change what you want.
So the Python heap by default is a min heap.
Okay, great. So that works for me. So yeah, it looks like it's a library, so it takes like a heap input. So you have to keep calling heapify on it. So okay, so I guess we just start with a blank list. So for now, I guess I'm just going to define a new function.
Yeah, you can get rid of these two.
So, and then points. Just gonna write down the stub here. Okay, let's think. So we need an empty list first to. Oh no, okay, that's already our function definition. So I could just I'll use this, and I'm gonna make a helper function to get the distance to the origin. To origin. X int. Maybe it would just be something like this. X. I think it right in Python it should be this. Right. Okay. Square root. Okay. Let me just look up Python. It should just be math.square root. I have to import that. Float cannot be. Oh, okay. Yeah. I guess I might have to use a float here. Right. I guess I forgot to ask earlier. So are these points? I guess it doesn't really matter. The only thing that matters is do we want an int output or does it not matter? Like, can we return? Oh, right. No, no, no. That doesn't matter. We just want a list of the points. So if I assuming if the original points are all floats, then we should just return the m closest points in floats as well. The original ints, we should return them in ints. So that shouldn't matter here. So just for the calculation, it's fine that if everything is like a float or because we need it for the I guess the square root. Okay. Heapify. Okay. Yeah. So we have this. We have the heap router. Okay. So let me see. Is there anything wrong with this? So just this is the Euclidean distance function. Okay. This looks fine. Okay. Right. Okay. So I'm just gonna have to think. I need to step through. So we're given the list of points. So we need to do minimum one pass through. So then at each iteration, we are going to push a point. Okay, no, I should write this down. Iteration, iterate through all points. Okay, so we have to push it into the heap no matter what, I think. Push. Wait, do we want to push this into the heap? Okay, so we push into the heap and we heapify. Does the heap actually maintain the top m closest or smallest elements? Because I know heap only loosely sorts the elements, but does it actually maintain the top m smallest here? Let me think about this. So if we had pushed, okay, so I'm going to just work with single digit numbers for now, just to so I have an easy example. So let's say we do uh okay, sure. We have some okay. So for now I'm just gonna treat these numbers as in the smallest number comes first. So the -1 would be the smallest, and then 1, and then 2. So I gotta think if I push this onto the heap, first iteration, our heap has 1. Second iteration, we have 1, 5. So these are still the smallest numbers we've encountered so far. Let's say that m is 3. 1, 5, 4, and then we keep going. So here is when we have to start popping something out of the heap. Oh, okay. Right. Okay. So I think we might have to use a max heap. I just realized because the heap, we need to get rid of the largest numbers. We want to maintain the top m smallest number. So, because when you pop off from a heap, the top number that gets removed is actually the smallest with the min heap, which is what we don't want. We want to keep the smallest elements. We want to get rid of the largest. So it would make sense that we actually want to use a max heap here. So I just need to update this. Okay, so we just need to remind ourselves to use a max heap later. Okay, so then we get to this step. If it was a heapify, okay, so then this would be this 5, 1, 4, just rough ordering 5. So here, when we call this, we check the size of our heap, and we know that it's over the limit. So what we're going to do is we need to pop off the max because it's a max heap. We get rid of that. And then is this okay? Does this give us the top end? It will always remove the maximum number. Okay. I think I'm just going to try to finish this example to try and convince myself and see if it does actually give me the top m smallest numbers. 1, 14. Okay, right. So we're right here. I'm not going to worry too much about the ordering the list. I'm just thinking of when we're popping off elements. So 1, 4, 2. Next, we push 12, and now we've exceeded capacity. We need to pop out a number. We need to pop. It's going to, when it heapifies, it's going to move 12 to the top. And then we're going to get rid of 12. So 12 is gone. And the next iteration, we add 15. We heapify again. 15 gets moved to the top. 15 gets popped off. So 15 is gone again. So, okay, it looks fine so far. And then here we go -1. -1 is the smallest. So the top of our heap right now would be 4 after we call heapify, after pushing -1. And a 4 gets popped off. And then we're left with 1, 2, and -1. Okay, so I feel like this is fine. So if m was 3, 1, 2, -1. Yes, these are indeed the m smallest elements. So I think this approach is fine. I just need to remember to use the max heap. Okay. Yeah, so I think I'm ready to start coding more. So heap. Let's think. So heap needs to look at the Euclidean distance. That's what we use the comparison function for. So okay, because I need to keep track of both the points and the Euclidean distance to the origin. So I would think about using like maybe like a pair tuple. But I need to make sure that the heap actually heapifies or like sorts the elements by that by the Euclidean distance properties. So I'm going to look up the how heap, because I believe in Python some sorting functions like dictionaries, they'll just look at the first element of the tuple if the input elements are tuples. And it should, if I put the Euclidean distance in the first part, it should evaluate and sort by the comp. So sorts objects the same way in list.sort does. So just define a comp method within your class definition. Okay. Heap according to this, you can use tuple, and it will sort by the first element of the tuple. So if you don't want, you manually extract. Okay, so it seems like the heap will just work on tuples. So contains list of. So I guess the data structure here will look something like this. Including, and then if the heap works as expected here, it should just sort by the Euclidean distance, will just be a float here. So I think that's fine for now. Okay, I'm gonna start writing out the for loop. Okay, so let's think. So we need to add distance. Yeah. Add the distance. Right. So we need to do. I think it was something like heap q dot heap push points. Okay. So we push. Oh right. Hang on. I need to make sure I'm initializing it as a max heap. So I'm just gonna look up how I do this real quick. Python initialize max heap. Uh, heapify max. Okay, so the function, so it just seems like whenever we use heapify, we just call the heapify max function. Okay, so that seems fine. But then heap insert, does that just, because when you heap push, um, I think this might do the heapify for you. So I think what I'm supposed to do here is actually just push it into the array, like just straight up push it in, and then I call heapq dot heapify max like this. So I think it would be something like, okay, so we need to end, or oh, right, okay, so per point equals points I, okay, and then we're going to do this. That would be the x coordinate and the y coordinate. So append this. I believe when you create a tuple, it's just like this. So that's the result of that, and then points. Okay, and then that's right. This should be parent points. So this would just be a tuple of this. I'm just going to double check this is how you make a tuple. Python tuple. Right, yeah, it's just inside curly brackets. Okay. Or I mean like brackets. Append, okay. And then we call heapify max. And then here we need to check off largest element. And then here we do, I believe we can just do like equals m. It's m, and then keep q dot off. And I know it's I saw the function earlier. Yeah, let me just double check again. Where the max heap? Heap pop max. Okay, so it's heap pop. Oh, okay, so it's not autofilling right now. Wait, so heapify max is this? Heap. Let's see, heapify max does when I do the pop. Okay, so There's no heapify pop function. I feel like I might be missing something with how I'm supposed to be using the heap. Let me just look for like a more in-depth use case somewhere so I can just copy it. Python max heap example. Should be at least one, right? Let's see. I keep finding implementations except instead of the actual like library. Uh, okay, so heap max push index to update. Um, Max heap. Hmm. Maybe if I just look at the actual function definition, it'll be faster. Oh, I guess there's no documentation here. Okay, let me just look at the official documentation.
Yeah.
Heap
So
queue.
Python does not have a max heap. All heaps in Python are min heaps.
Oh, okay. Okay. If they're all min heaps, then I could probably just use a hacky fix where I just return the negative square root like this. So then the like the largest number would become the smallest number. So I think that also works, but it is kind of hacky, but I think it's good enough for the purpose of this interview. So heap q dot. Okay, so I'll just do this for now. So return negative math dot square root. Okay, heap dot heapify, and then I can just do heap pop. Right, I could just do heap push here then. I think I have to do this, so it can just be heap q dot heap push distances, and then oh, I shouldn't have gotten rid of that tuple. Let me grab this list and then item. Okay, that looks fine. 0, 1, f length, m pop distance. So this should get rid of the largest element. Okay, okay, that looks fine. And then we would just return, right? We only want the points in the end, so we need a way to actually I guess get rid of the points. Let me think right now. Because then we'd have to iterate through the entire heap and just grab the points, which is fine if m is small, but if m is roughly the same size as n, because I'm assuming the actual distance or like the values of m and n would be something like this. Is this correct?
Yeah, that's right.
So like, okay, yeah. So I kind of want to avoid iterating through it again just to grab the tuple. Um, so then that would mean that we would have to actually, I think we would have to initialize some second data structure alongside and then kind of manage like a list, like a return array with just the elements of the, like just the points, because we don't want a tuple, we just want a list of points. Um, I gotta think about how I'm gonna do this right now. Well, actually, no, I should probably just run this and make sure my actual algorithm works first before I worry about making further optimizations. So I'm just going to run this first and see how this works. I think I'm going to need a main function. Let me just grab one real quick. Okay, so it's just literally just this. Okay. I'm just going to, I don't know, insert some random data points. Okay, and then just at the top 4 points. So we're gonna call this. So it's just gonna be the input is then points. Okay, and then let's print this out and see what this looks like first before we get ahead of ourselves. Drop that. In red format. Oh, what's going on here? Finished in 1 point. Okay, so it's not really printing anything right now. Did I miss something right now? This main. Oh, no. That's not the actual main. I just realized it needs to be right. It's like this, and then you run main from here. So I believe it's this. Okay. Okay, so it's still not printing. Oh, okay, there we go. Okay, now we got a 1, 2, 3. Oh, okay. Okay, so wait. So we got 1 point, 2 points, 3 points. Okay, so our M is 4. That's kind of weird. Let me think about this. Why are we returning 1 point less? Um. Okay. This should be M plus 1, right? Because the array should be size M. Because then if we keep popping, as soon as it reaches size M, it's going to be always 1 less. Okay, so let's see. Are these the smallest? 5, 4, 0, -2, right? The heap doesn't necessarily return it in order, but so 3. I should actually double check this to make sure that these points are actually the closest.
Yeah, no, that's
So
fine.
I would expect to see 0, 0. I would expect to see 1, 2, 4, 0, and then maybe okay, wait, hang on. So for sure we expect 0, 0. This is for sure. 1, 2, yeah. Maybe I should just change one of these to 2, 1, so it's pretty obvious which points are going to be the result. So 0, 0, 1, 2, 2, 1. Okay, and then I'm just gonna change M to 3. So the output is a bit easier to read. So 1, 2, 2, 1, 0, 0. Okay, so the behavior looks as expected right now. We are getting the smallest values. Maybe let me try a negative value. So, okay, yeah, so the Euclidean I need to test that the negative values are working properly for my Euclidean distance. So, like, let's do -3, -1. So this, wait, hang on. So what am I trying to test here? I'm trying to make sure that negative values are not being treated as the smallest. So like -15, like Euclidean distance on the, like you shouldn't have a negative Euclidean distance. Um, right. I just need to make sure that it doesn't treat -15 as a value smaller than 1. It should just be, like whatever is closest to, like smallest in the absolute sense. Um, right, wait, okay. I don't even know why I'm worrying about this. The Euclidean distance function should be fine. Yeah, okay. So this looks fine for now. So I think I'm going to go back here and see if there's a better way to, I guess, optimize the actual returning here. Because I don't want to just iterate through and like remove the point from the tuple and then like push it to a list. So that could be potentially pretty expensive. So what I need to do is I would have to maintain like I think maybe I guess a set wouldn't work. So what would work here? Um I'm thinking maybe if there's a way I can directly pass a comparison function to the heap. So then it would just do the Euclidean distance thing for me, and I don't even have to store the Euclidean distance. I think that would be the most elegant solution here. Um, So I'm just going to look into see if I can do that. Fine. TQ sorts objects the same way. List.sort does just define a comp within your class. But then we need a class. So then, okay. Let me see if there's like an easier way to do this. In heap. Hmm. Okay, wait, before I okay, yeah, no, it's fine. Okay. Um Python custom X DQ comparison function.
What's the goal here?
Um the goal here is to essentially avoid because our requirements for the function is we want to return a list of the m smallest points, right? But right now we're returning the m smallest like tuples. Like the point is inside a tuple. So to actually extract the point from the like the list of tuples, you have to iterate through each one and like take the point out, which can be potentially kind of expensive. So I'm trying to see if we can get rid of this step. Like it doesn't change the asymptotic runtime of the function. It would still be big of m log m, I believe, but I just want to see if there's like maybe a way to avoid this as well. Does that make
For
sense?
now, don't try to avoid it.
Okay, yeah, sure. Let's just not worry about that for now then. So let's go through the I'll just do like the brute the kind of the dumber solution. Or I mean like just grab the tuples, the points from the tuples, right? So so should be iterating through this. Uh just do this. And then it would be something like parent array dot end distances I and then the splitting distance the first one, so it should be this. So let's just run this and see how it looks. -1, -1. Okay, this looks as expected. So in the case where you have like point like 1, 2, and 2, 1, they have like the same Euclidean distance from the origin. Doesn't matter which one we return.
Say again.
In the case where 2 points are like tied, does it matter which one we return? Can we just return either one?
You want to return the one that appears earlier in the list.
Earlier in the list. Okay. Let's see. So we return 1, 2. Okay, so 1, 2 comes earlier in the list, but we actually return 2, 1. Um, okay, so this is kind of a weird edge case. It's actually kind of difficult to deal with. I just have to write this down. If 2 points I turn the one closer to the return the one that comes first. Okay. Okay, this
Actually,
is actually
for now, let's forget about this. So you can return anything.
okay. So we can just return anything. Then I think my solution right now is fine. Do you have like you want me to like just use ChatGPT and like generate more complicated input to test
No, that's
or
fine. I think it's correct as well.
okay.
Can we go over the time and space, please?
Okay, yeah. Um sure. So get distance to origin. Um unless we're working with some like freakishly large numbers, this shouldn't be much of an issue. So this is just constant time here. Constant time. Okay. Initialization here. This is constant time. Um Yeah, so for the for loop, we're paying O of n, loop through the entire list here. So push the point. Wait, hang on. So I'm gonna write this down. In iteration. So for each iteration, grabbing the point is constant time, push it onto the heap. So this is potentially operation heap pop. Heap pop, because when you pop an element off the top of the heap, you have to heapify down. So that's also, oh, that's the same operation cost as well. So that should also be log of m. So then this would be n log m, okay? And then at the end, we just, all right, hang on, I'm gonna write down the total runtime for this loop here. So this would be O of n log m, okay? And then here, let's see. So I in range of length distance. Okay, so we're just iterating m iterations, and then we just do constant time operation for each. So that's just total cost is just in the end we have plus O of m, and I think asymptotically it should just be this is the total runtime of the function, so it should just be n log m. So the optimization we achieved here without just sorting the entire list with like the dumb solution is that it becomes log m instead of log n, which is like a potentially a very big speed up if m is significantly smaller than n. And as for the space complexity, let's see. So we initialize a heap, and so okay, so the heap is always of max size O of m. So I guess let's just write this space complexity here. It's just going to be let's see. So the heap is always of O of m, right? So the heap is. Do we use any other stuff? Okay, so I guess we technically use this list as well. Um, Asymptotically, it's the same. I don't know how the Python compiler exactly handles the freeing of old arrays. Oh, okay, no, so I guess it wouldn't be freed here. So our total cost would be 2 of 2m as O of 2m, but then that would still be O of m asymptotically. So our space complexity is still O of m, I believe. Um, yeah, I think this looks fine unless there was anything else I missed.
Okay. Yeah, sounds good to me. I think we have time for maybe one or two quick follow ups. So let's just run through those as well.
Yep.
Um, so the first follow up I would say is, if I can guarantee that the size of m is proportional to the size of the points, would your approach change?
All right, could you repeat that again? Like, what do you
Yeah.
mean by m is proportional to the size of the points?
Yeah. So m is dependent on the size of the point. So let's say m is half the size of the list, and it's in
Okay.
proportion, which I don't tell you ahead of time, but I can tell you it's proportional.
Okay, so it would be essentially equivalent to n divided by something,
Yeah.
but it's like proportional to n. So
Yeah.
then that would just make it asymptotically n log n, no matter what. But so you're asking if my approach would change with this, like, I guess, okay. Like, would it actually change my implementation, you mean?
Yeah. Like if that was the restriction that was given, would you still have written the same algorithm?
I guess it depends on how much we value space because we do use a little bit more memory here to make this runtime optimization. If it turns out that the runtime is going to be asymptotically proportional to n anyways, and for some reason, we really cared about saving memory, we could just sort it because then that would just be n log n anyways.
Mm-hmm.
It's asymptotically the same. And then if we sorted instead, we would just use the memory in place. And then we wouldn't even have to initialize the heap. So we could save some memory in that case.
Okay.
So this is kind of like a trade-off between if we value runtime more or if we value memory more in this case, I think.
Okay. Makes sense. And then let me think. Okay, and then I guess another one is, let's say instead of two-dimensional points, we had k-dimensional points. If you had
Okay.
k-dimensional points, what would change? The complexity wise.
Okay, so k-dimensional points is going to, assuming like, if it's like some, I don't know, like machine learning data, k could be like very large. It could be like 1,000 or something. That's going to definitely change our Euclidean distance runtime. So let me just think about this for a second. So I believe I just need to remember how because then it would be no longer, is it still Euclidean distance? What's the distance function in 3 dimensions? It's not, is it cube root? Let me just double check that. Um, Euclidean distance in dimension. Okay. Uh, okay, so I just searched this up and it says that Euclidean distance might not be a good metric in high dimensions.
It's still square
So,
root. It's still square root. It's the square root of the sum of squares of all the
okay,
intermediate
yeah.
dimensions.
Um, I think in this case, I am aware that there are other distance measures that we can use, so there might be a better one. I'm just gonna do a quick search and see if I can find something better than Euclidean distance.
No, we can assume it's Euclidean. That's fine.
Okay, so if you just want to know the change in the runtime rate, okay. So it would just be k dimensions, so then this would cost O of k, which is our number of dimensions. So then here, we would have to pay, okay, let's see, we call this once per loop iteration. So then that would just add, let's see, we just pay this one. So then this, instead of n log m, this would become n k log m, I believe. And yeah, that looks about right. Our space complexity would also obviously go up. We're definitely using a lot more memory now. So then this would be km or mk. Yeah, this is assuming we
Okay.
still use Euclidean distance.
Okay. Yeah, sounds good. Let's end the mock here and let's go into the post game interview.
Okay, sounds good.
All right. So I mean, usually open these up by asking you how do you feel, what went well, what didn't go so well, in your opinion, and let's start from there.
Okay. I think I got a little bit nervous because you were silent for a while. I felt like I might have done something wrong, and I also felt like my train of thought sometimes when I was just talking was a bit incoherent. Like especially when I started talking about how I was going to optimize this part where we like get the return array, I think you were kind of lost on like what I was trying to accomplish there. So I definitely could have been a bit more clear on that.
Mm-hmm.
And I also just feel like I could um maybe a bit nitpicky. I could just brush up a bit more on Python syntax so I wouldn't have to waste so much time on looking up like, oh, like what how do I get like a max heap or min heap? So you have to just like straight up come out and tell me like every heap is a min heap in Python. So
Mm-hmm.
I used quite a bit of time on that, which I think I could definitely could
Yeah.
avoid.
Yeah. 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 Um,
But overall, I think I'm like pretty happy with my solution. I think
yeah.
I walked through like my thought process. I guess like another kind of annoying part is I didn't really have a good example prepared ahead of time.
Right. Yeah.
Um, but like I guess in like an interview, usually when they copy and paste the question to the IDE, like they would have an example scenario prepared for you that you can just look at, right?
Yeah. Usually, if they do copy and paste it, they will, but not
Hmm.
always. They'll copy and paste it depending on what they're trying to test. So just be aware of that.
Okay, right.
Um,
Yeah, I think that's
okay. Yeah.
pretty much it.
I think you had a pretty fair and generous assessment there. So I think I'll just add on to that by saying a couple notes ahead on my side, and I'll send you these notes after, so you don't have to write anything down here.
Yep.
Um, yeah. So first thing is first is I think you have a pretty good system for organizing thoughts. That's the first thing I'd say is a strong point. That could be your method taking notes, method writing down examples, etc. Testing things. That thing is, I think that category I would say is a strong suit. So keep that up and keep developing that system for yourself.
Hmm.
That's something which is usually hard to kind of cram. So good. It's good that you have that kind of built up.
Thank you.
Um, Now, a couple of things off the bat, I think I wanted to say, not about just generally, just like not specific to this problem, but just in general. And again, please feel free to like pause and question if anything happens.
Hmm.
The first thing is about the edge cases, right? And as you have noticed, there was an edge case you did miss, which is what if there's a tie? Okay.
Right.
Now, the thing about this is that this is not the only problem where you can have a tie. Okay. Many problems can have ties, right? And
Hmm.
so this is maybe a potential augmentation to your system, which is if you ever get a problem which has the ability to have ties, you should be thinking about in your head, hey, how do I resolve ties? For a lot of problems, it's trivial. There's a very obvious answer to how you do a tie. So for some
Hmm.
problems, it's less trivial, like this one, for example, where you might not know how to resolve a tie. So
Right.
there's a lot of these things that happen, like these edge cases that you need to think of, and I think it could be good to embed these edge cases into your system, right? To kind of make sure you don't miss that in the future. Because in this
Right.
case, by the time you real and by the way, I was surprised you actually caught that at the end. Because usually, if you don't catch it at the beginning, you just never catch it. But by the time you
Hmm.
catch it at the end, it's too hard to
Yeah,
fix
it's
it.
it's
You
already
can't.
too late.
Yeah, like this by the way, and the solution you came up with, by the way, is a good solution. It's a good solution if you don't have to resolve ties, right? So,
Hmm.
so by the end there, I just wanted to see. Okay, you thought you caught the edge case. You saw there was something going on. You were coming up with an idea. It wouldn't have worked, by the way, but you were coming up with an idea, and I just had to stop you right there because it just would be a waste of your time, right? So,
Okay.
so again, you don't want to put yourself in a situation where you have to scramble at the end. That's not going to help you. And by the way, if you scramble at the end, most of the time you won't even get it either, right? So
Right.
just be aware of that. That could be a very costly mistake. Okay.
Hmm.
Um, another thing there, and I want to just kind of just mention this, and you did mention it earlier, but I think this is really important. If you're going to interview, like Leetcode interview or whatever interview, and you're picking Python as a language, the interviewer is going to have a baseline expectation for what you know, what you don't know. Okay.
Right.
Now, it's okay, for example, to not really know the heap syntax. You can search it up. That's okay. But I feel like there were some other things there that was a bit maybe more on the edge. Like for example, like I mean the first thing I would say there's a tuple initialization. That was a bit surprising. I would expect people to know how to do that one without having to search. There was a comment you made about how tuples are compared. That I would say is also quite important to know.
Okay.
Um, so
I did believe though, like I said the right answer.
you did say
Like
the
it
right
always,
answer.
I just wanted to double check just in case.
Right. I mean, and here's the thing, right? So, yeah, it's not wrong to double check, but again, you have to be cognizant of the fact that you are picking Python to do this task, right?
Hmm.
And this is not like comparing tuples is not an arcane concept in programming,
Right.
and so that's just all I'm saying is that that's gonna peg the interviewer's level of confidence in you at a certain level, right?
Hmm.
Like it's just a perception you're given to the interviewer. Right now,
Okay.
now I will
Gotcha.
also add that yes, it's better to double check and be right than to not double check and be wrong. Right? I'm not saying otherwise. I'm just saying if you had to double check that, the interviewer just going to put okay, well you know at most you're at this level, right? And so that's just the impression you're going to give off.
Okay.
And that by
Gotcha.
the way, and that you might like that's not like that information isn't unique to this problem, right? That's not a heap question. That's just a tuple. Like that's just a Python question, right?
Hmm.
And so like again, like just be aware of that, right? And the heap details here, I would say, like it's important to know a bit about the heaps. Like you seem to know a little bit about the pops and the pushes. There was a couple things that were a bit concerning. The first thing was that Python is a language that doesn't have one of the two heap types, and so if you want to have the max heap, you need to invert the weights, which you did do, right? But you need to
Hmm.
cache ahead of time,
Yeah.
right? Now, for example, I would say a reasonable question would be, "Oh, I forgot what the default heap type in Python was. Can I search that up?" That would be totally fine because no one needs to memorize that. But if it's given to you that um, it's just a min heap. It's what it is. I don't want you to be spending 3, 4, 5 minutes searching up how to do the max heap variance, right? And
Yeah. Right.
again, this is a bit of a note there as well, which is when you were using the underscore heap push underscore max, the underscore in Python means it's a private method, and so it's actually not available. So those are the kind of
Oh,
things that
right.
the interviewer would be like, oh, okay, this person probably isn't very familiar with Python, right? So just be aware of that. If it's a Python role, that'll be not good. If it's not a Python role, that might be less not good, right?
Okay. Right.
Okay, so a couple things at the beginning as well. So you had pretty good. So I think this is a common thread throughout the interview process here, which is that you had good time analysis. That the time complexity was always correct. It was always good. The space is a bit weaker. We'll get to that, but the time complexity was always good, and so that's something which you should continue to continue to practice and acknowledge trade offs in, right? One thing about the space I wanted to talk about here was, and this is not a problem, but you automatically decided to trade like space for time to get better time, worse space, right? And that's typically okay. That's typically a good assumption to make. However, it's oftentimes good just to check with the interviewer. Hey, I've got these two ideas. I think this is the case for that. I think this is the time and space for option A. I think this is the time and space for option B. Do you think I should proceed with option B? I think it's got better time. I want to go with that.
So
That's
you
something.
think I should have presented like the two approaches first to the interviewer and asked them which one they preferred for this
Yes,
problem?
in this case, because you clearly knew the time and space of both,
Okay.
right? And so
Right.
if you know, if you have a good confidence, you have a good grasp on that trade-off, it's a strong signal to just say it right off the bat, because then the interviewer can say, oh well, this person already very quickly grasped what the trade-offs are. And so it's
Hmm.
good to kind of bring that. Now, if you don't know, if you can only think of one option, or if you don't know the time and space of the other one, you can keep a higher level. Say, hey, I have these two approaches. I don't know which one to take. I'm going to plan on taking option A unless you say otherwise, right? So,
Hmm.
but if you're able to kind of come up with those numbers or those expressions, that's a very very good sign, right?
Okay. Yeah.
Now,
I think, yeah, I am kind of in the habit of just assuming that we should always prioritize on runtime, but
yes,
yeah,
I mean, and that
definitely
that
I
is
should.
almost always true, but sometimes it's not, and it's not about showing off that you know the. It's not about that. It's about the format. It's about like telling the interviewer, hey, I'm very organized. I've got these ideas. Here's what I'm gonna do. Right? Like here's what I
Hmm.
plan on doing, which is a time optimal one. And then if they want to steer you otherwise, they can. Right? So it's about bringing the interviewer to your world to let them know what you're thinking of, and letting them interrupt you and letting them correct your course if they so choose. Right? That's not a negative thing. Think of it that way. Could that be construed
Hmm.
as a negative attribute? That can't. Right? So that's totally fine. Um,
Okay.
Now I did want to talk about a bit about space, because your space complexity here wasn't exactly right. The space complexity for your original solution is correct. So it is O of m, which is the size of the heap for that. However, the follow up question wasn't quite answered correctly. For example, when I said, "Hey, if you were to well, I mean, you said this. Hey, if n is proportional to n, we would always just sort the solution, or sort the array." Um, that wasn't exactly correct. I think like your reasoning there, because you would say that because your implied topic was that the sorting doesn't have a spaced overhead, which is not really true. Sorting still does have a space overhead. In this case, if you're using default Python sort, which is tim sort, it would be O of n as well. And so
Oh, okay.
and that's true
Aren't
for
there sorting algorithms that would just sort the array in place though?
there are, but they're usually not as efficient. You can do, for example, I mean, there are algorithms, but you have to clarify that, and that's not always the case, because in this case you're using a language you're not very familiar with, and the interviewer's not going to have confidence in that, right?
Okay.
Um, Let me just quickly check my notes again. So I mean, it's just one of those things where you have to just mention it, right? Because if you're using default sort, which is what you would have done, that would have been O of n as well for space. Now, for example, because points are not object, well, there depends how you define them. In other words, like you can use quicksort instead of tim sort. Quicksort, I think, has login space, so you could use that as a justification, for example.
Hmm.
But you didn't say that, so
Okay.
so
Yeah.
that's not gonna exactly work. I don't. Yeah.
Okay.
Yeah. And then one more thing about the end there about the space complexity with k dimensions is that the space actually wouldn't scale with k, right? The space wouldn't scale with k because the distance is still a single number. So you wouldn't be storing k distances. It'd just be still one distance. So the space complexity wouldn't change. So that's a detail you missed at the end there as well.
But like for our return array though, we're essentially creating a copy of the m smallest elements, like the actual points themselves, right? Wouldn't this take up mk space?
Yeah, that would take up nk space, but that wouldn't be due to the Euclidean distance, and that's part of the return. So that would be something which you would like. Yes, the algorithm will still take mk space. That is correct, because that is the size of return. That's the bound. But your justification for I think the justification you used was pertaining to the distance, which I perceived as this, which is not the case. Like this is the part you were pointing towards as you were saying the space. So
But with our current approach, where we
yes.
store both the point and the distance, wouldn't it
Oh, I
would
see what
be
you mean.
mk, right? If like if we optimize that away where we only store like the distances and we could just grab the points in the end, like that wouldn't be it wouldn't
Yes, no,
scale
actually,
completely
no,
right.
actually, no, actually, I got confused. You're right. This is still like even this is still MK. The part I got
Mhm.
confused by was your was I got ahead of myself there. I know we're a bit over time there, but if you have a bit of time, I want to chat with you a little bit about what I was just gonna get to as well.
Yeah, for
Um,
sure. I have time.
cool. Which is the tie break, right? What I was gonna get at there was actually the fact that um, the solution most people use to tie break is not to push the points.
Mhm.
Sorry, which is this point, which is not to push the point onto the heap, right? And the reason you don't push the point on the heap is because you actually don't care about the point. What you actually can push instead is the index,
Ah, okay.
and that would
I
get
see.
around this being mk space. That would just be m space then, the distances I mean.
Right.
And the way
Okay.
you would do the tie breaking is that instead of just comparing the distance, which is this field over here, you would put in a second variable in the tuple for the index,
Hmm.
and that would be used as a tie break comparator.
Okay. Yeah. Gotcha.
So
But like
that's the
the
part I was
actual
thinking about. Yeah. Sorry. Go ahead.
right. Because I still think the tiebreak is not necessarily this simple. It's kind of just whatever element gets floated to the top of the heap when you happen to call, I think, heap pop. Um, I think we might have to do some kind of override of the heap queues comparison function in this
You
case, though.
uh,
Correct me if I'm wrong.
I mean, so yes and no. So that would open another can of worms because that would really depend actually. So this is a good point. That would actually depend on precisely how many ties there would be, but we don't actually need to override the comparison function,
Hmm.
and that's simply because it's a monotonic truth that if we had, for example, like let's say we had m equals 3, like your example, and we had two ties, we only care about the best tie, right? Like of all the tied points, we only care about the best one or the best two of them. Because if we were to find a point that's closer than the ties, then we only need to care about the best one tie. So we wouldn't actually need anything as complex as overriding the comparison function for the purpose of solving
Okay,
ties.
wait. I'm not sure I follow. So by best tie, like if they're tied three ways,
Yes,
for example, like they would all have the exact same distance. So, like,
they would, yeah, but they would have different
so
indexes,
what
right?
what do you mean? Oh, right. Yeah, yeah. Okay. Right, because we only care about the smallest index. Okay,
Yep,
that
you
makes
would put the
sense.
smallest index first. Well, it
Okay.
doesn't matter. That's what I said, but it doesn't actually matter what order they're in as well.
Hmm. So like how would we because like inside the heap, like let's say we have a tie, right? So let's say we have one point already with like some distance, and then we have another point further down the array
Yep,
with a different distance. And then the first point is already in the heap.
yep.
So how do we actually find that points index? I guess we could keep like a hash map
I mean,
of like
you wouldn't
the
need that points index. You would encode the index into this. So, for example, let me just do this for you. So, um, distance equals this. What am I missing? I'm missing that. So you would be doing dist I as the encoded comparator.
Oh, okay, I see. Because we're comparing the entire tuple, which includes the distance and the index. So the okay.
Yep.
Okay, wait, that's really smart. I didn't think of that. Okay, that makes sense.
Yeah, there's a reason that's not part of the default Leetcode question.
Mhm.
Okay,
Okay,
so
so like the comparison function in Python, it would just take the first element, but then if you like bundle several things together in a tuple, it will just take the whole tuple.
what's still the comparison logic for tuple is as such: compare the first element of the tuples, and if there's a tie, compare the second, and if there's a tie, compare the third, etc.
Okay. Okay,
So
I'm actually kind of not too clear on how the tuple comparison works, so I definitely need to kind of read up on this a bit more, but this is very helpful.
yep,
Thank you.
you are welcome. Um, Otherwise, there's some notes I'll send you later on. But yeah, this problem gets quite advanced. I'd say for today's kind of level, we kind of only touched base on like the medium area. we didn't get to the kind of the harder follow-ups. But
Hmm.
just be aware that like yeah, I think a lot of the hold up here was your unfamiliarity with Python. I think if you were faster
Okay.
with Python, like because it seems like you knew the algorithm for a long time, you just couldn't write it, right? That's actually rarely the bottleneck with Python. So I would suggest, yes, using Python is good, but you should really try to get familiar with it so that becomes less of a bottleneck.
Okay.
Because a lot of
Sounds
these
good.
problems, especially, and you can, by the way, you can sort of metagame this a bit, right? If you're going to a company interview where you know they're going to be asking more difficult questions, and they're giving you
Hmm.
this medium question up front, because the question you mentioned, the top K numbers, that's also medium, right? Like
Hmm.
if they're giving you a medium that sounds like a medium, you should know that that's not the real question, right? This is either a warm
Right.
up or there's a follow up that makes it not a medium. And so you should be really trying to get through the question as is as soon as possible, right? So so
Right.
so
Because I
just
have
be
to
aware
make
of that.
space for the actual follow-up.
Yes, and it's not just make space. You have to make enough space because if you finish it, let's say it takes you 35 minutes to code it up, right, to up to here, and
Hmm.
then the follow up is a hard question that makes this hard. For example, let's say what if we make this an online algorithm? That's a typical follow up for this, right? The interviewer will not have confidence that you can do that in 10 minutes, and so they just won't ask it, right? Because you'll
Hmm.
have a bad experience. They know you won't pass, and so they'll just fill it up with some like random ass shit instead. So you have to just be cognizant of that. That like you have to be fast. If you know they're gonna be asking harder questions and it's an easy one that comes up first, you have to be fast. That's the only thing you can do for yourself. So just be aware of that.
Okay. Sounds good.
Cool. Any
You
questions?
mentioned you mentioned the hard follow-up is like turning the algorithm into an online algorithm. So could you explain a bit what that means?
Yeah. So there's a couple follow ups. Generally speaking, the online algorithm goes as follows: define a class that does this, and also a second function. To define a class which does this, and also include two functions. First function, add point. Second function, query k closest.
Um, okay,
So that
so
so it's the
is it
same.
essentially ask? Sorry, go ahead.
Yeah, so it's a very similar premise, except now you can modify the points live. You can add and remove points, and then you can also query the m closest points, but m changes with every query. M can change,
Okay, I see.
and then that's like a pretty standard like for in new grad kind of stuff like a pretty standard kind of level, and then a real hard follow up there, which is unreasonable to ask, but is actual hard follow up, is k closest, but to a point in the already like in the list already. So not to the origin, but to another point.
So we're not comparing against the origin, we're comparing against some other point.
Yes,
Okay, so I can't immediately see why this would be a super hard follow-up.
it's a
Is
super
it
hard follow up because it requires a complete rewrite of the data structure, and it requires you to know some pretty advanced tree and graph and potentially geometry if you want to get optimal.
okay, gotcha. Yeah, I guess we don't have to time to open that can of worms.
We don't have the time. We don't have the time, but you
Yeah.
can go search yourself, like a quad
Hmm.
tree or a KD tree or a KNN tree. So you can go search those up yourself. But yeah,
Okay.
so there are advanced questions that are follow ups for this kind of thing. But again, like a reasonable follow up would be turn this online or M can change.
Okay, sounds good.
Okay, that's all the time we have for today. Thank you for participating, and hopefully we'll see you again soon. Take care.
Thank you so much. Have a good one.
You too.